Okay, we're back to finish up the graphing notes, and I noticed that a few things at the top got cut off last time, so if you want to pause and just write those down, they're up there. Okay, so once you've got that done, we'll look at this slightly more complex graph down here in the middle of the page. And it looks more complex because it is. I made it specifically so that there were a lot of different things that we could look at. But one of the things that you need to start realizing when you have a graph like this is that every individual bit of this graph can be broken up into this graph can be broken up into smaller parts that you can, and then you can analyze the parts, and you'll see that the parts are really not so different from what you're used to. We have 5 or so questions. I kind of inadvertently made the first 2 questions the hardest ones. So we're actually going to start down here with the question, approximately when did the object pass the origin? So first thing we need to do is we need to figure out what type of graph this is. It's x versus t, so position versus time. So our fact for knowing how to figure out the position from a position versus time graph is simply, okay, well, all you have to do is look at where the position is 0, where the position would be at the origin. So I'll take my straight edge and I'll just lay it right across the x equals 0 line, and we see that the position of the object hits the origin at, it seems, about 3 different times. One interval right here, A to B, then right here, and then right here. Okay? So, when did the object pass the origin? We'll say from interval A to B. I guess it's not really passing the origin, but it's just at the origin, but, you know, similar thing. We have one right in the middle of the stretch from D to E. It looks to be a little bit to the prior side of 15, so let's call that 14 seconds. Object is passing the origin, going from about 14 meters or so down to about negative 21 meters or so, have to pass the origin. And then from E to F, it goes from about negative 21 meters or so all the way up to, looks like about 18, positive 18 meters or so. So that's also got to be an origin passing. And that happens, looks like between 20 and 25, maybe a little bit before the halfway point. So let's say 22 seconds. Okay? So that's when it passed the origin. Now, during what intervals was the object stopped? Okay. Well, this is a slightly different question. Not when it's at the origin. Origin means the position is 0, but stopped means when is the velocity 0. And if you remember, on an x versus t graph, the way to find the velocity is to look at the slope. So if we want a velocity of 0, that would mean we want a slope of 0, and that occurs when you have a flat stretch. Not necessarily a constant slope stretch, but a flat stretch, okay? Like this right here would not be flat. That definitely has a slope to it. But from A to B, that is definitely flat. C to D appears flat, and F to G appears flat. Since those flat sections are where the slope is equal to 0, and this is a position versus time graph, therefore the velocity is also equal to 0. And the object must have been stopped. So from A to B, from C to D, and from F to G. Those are all the instances when the object was stopped. Third question is an interesting one. Did the object have a greater speed during D to E or E to F? And this is a little tricky because it says greater speed. And we have to remember the difference between speed and velocity here. Remember that velocity is a vector, so direction matters. So it matters whether it's a positive or negative velocity. If you look at these two, D to E, that's a downward slope, that's a negative velocity. E to F, that's an upward slope, that's a positive velocity. So if this question had said greater velocity during D to E or E to F, you would say, without even hesitating, from E to F, because that is where the velocity is most positive, or is the greatest, okay? But it says speed, and speed does not have direction. Speed simply refers to how fast something is going without referring to any direction whatsoever. So if we're just referring to direction, you could be moving backwards very fast, you could be moving forwards very fast. The key here is we need to look for which one of these segments has a greater slope, or not a greater slope, but maybe the steepest slope. Because the steeper your slope, what that indicates is the more rapidly your position is changing in a smaller period of time. So, did the object have greater speed during DE or EF? I'm going to extend these lines a little bit. This is pretty steep right here from E to F, but I think you would probably agree with me in the argument, and you could do the math if you wanted to. You could prove that the slope, the steepness, is greater for D to E. D to E is definitely steeper. If you wanted to talk about this in terms of math, you would say that the absolute magnitude of the slope okay? The absolute magnitude of the slope of this position versus time graph is greater for d to e. And that's really what we're looking for when we look at speed. We're looking for the absolute magnitude of the slope of a position versus time graph. So the answer here is actually d to e is when the object is moving the fastest with the greatest amount of speed, because that is the steepest part of the graph, regardless of the fact that the object is moving backwards at this point. It's going from positive, it's going from positive positions down to negative positions. Okay, it is moving backwards, but the slope is the steepest, therefore it is moving the fastest at that point. I'm going to go up to the first question now. When did the object have a negative acceleration? Okay, so this is a position versus time graph. We have to think about how to determine acceleration here. We know the slope of position versus time tells us the velocity. And so let's look at some intervals we've already looked at. From A to B, C to D, F to G, we have slopes of 0, which means no velocity. The velocity is 0, the object is stopped, and we also know that when we look for acceleration, we're looking for changing slopes. So A to B, C to D, and F to G, there's no changing slope there during those intervals. The slopes are flat and they're staying that way. Also, from D to E and E to F, we have non-zero slopes, but are those slopes changing? The answer is no. Those slopes are not changing. They're constant slopes, which means that the velocity is constant during those points, which means, therefore, that the acceleration is 0. So again, how to find acceleration on an x versus t graph, position versus time? You have to look for where the slope, the steepness, is changing. And during none of those intervals, A to B, C to D, D to E, E to F, and F to G, is the slope changing. Okay? So that leaves us to look at B to C. We have a slope that's definitely changing. It starts off very steep and becomes not steep by the end. It starts off very positive and steep, and it becomes close to 0 by the time it approaches C. Now, is that a negative acceleration? A negative acceleration means that the velocity is decreasing. And for the velocity to be decreasing, that means the slope has to be trending towards negative infinity. The velocity has to be going towards negative infinity. Okay? Now, you might say, well, that's not happening here. We have positive velocity the whole time, and you're absolutely right. But you start off with a very positive velocity, very highly positive velocity, and the velocity trends towards 0. It's definitely getting away from positive infinity. It's going towards negative infinity. So I would make the argument that this is a negative acceleration because you have a velocity that is negative, or that is becoming more and more negative. Even though it's positive right now, your velocity is trending towards negative infinity. So when did the object have a negative acceleration? It's actually from B to C. And that illustrates a point that a lot of people fail to realize. Just because the velocity is positive, which it is because we have a positive slope, does not mean that the acceleration is also positive. A positive velocity simply means the object is moving forward. However, if that velocity is trending towards negative infinity, that means that there is a negative acceleration. And what that actually means, if your velocity and your acceleration have different signs, if the velocity, let's say, is positive and the acceleration is negative in this case, what that means is the object is slowing down. And that makes total sense because this object is moving very quickly right here. The slope is very steep of this x versus t graph, and the slope is basically 0 up here. The object slowed down. It basically stopped moving by the time it got to C. So, anyways, the only period when this object had a negative acceleration was from B to C. Now, you could make the argument, well, what about at point E? Or what about at point D? Or what about at point F? Okay, we're looking for time intervals here. We're not looking for exact points, okay? It's kind of tricky to talk about what happens at points because that's one instant in time. We don't deal well with one instant in time. We like to look at things over a period of time. So we're going to ignore those points. Last question for this graph. During what intervals was the object speeding up? Well, we just said that we have no acceleration, and in order to speed up, speeding up is a type of acceleration, we have no acceleration from A to B, C to D, D to E, E to F, F to G, because all of the slopes during those points, during those intervals, are constant. Constant slope on an x versus t graph means constant velocity. Constant velocity means no acceleration, so it can't be speeding up. From B to C, we just said that it's slowing down. So on this graph, there are no intervals where the object is speeding up. Again, you could maybe make the case that at point B or point E, we have an object that is speeding up. But again, we're not looking just at one point in time. That is a little bit misleading. Things don't change in an instant. They change over very, very small periods of time, but not instantaneously. So we're going to go with there's no interval during which the object is speeding up here. Okay? Now, that's how you can look at a graph like this. And just to kind of sum up, from A to B, we have an object that is not moving at all, and it's at the origin. From B to C, the object travels forward with a positive velocity, but a negative acceleration. So at point B, it magically gets this very high positive velocity, but it starts to slow down as it approaches C. It has a negative acceleration. From C to D, the object is ahead of the origin. It has a positive displacement, but it is not moving because that slope is 0. From D to E, the object moves backwards towards the origin, and then once it passes the origin, away from it with a negative velocity the whole time, a constant negative velocity, it should be said. At point E, it instantaneously switches to moving back towards the origin and then moving away from the origin once it passes it. This is a positive velocity the entire time, constant positive velocity. And then from F to G, it is motionless once again. Let's see here. Nope, that's pretty much all I want to say about that. Okay, so we can break these complex graphs down into one or more parts depending on how the graph features look. Okay, and that's something I encourage you to do for these complicated graphs. Last thing we're going to do, and on the next set of videos we're going to follow up with this, is we are going to look at different graphs of either x versus t, v versus t, or a versus t, and predict what the other two graphs would look like. So for example, this x versus t graph. How would you describe this? Thinking about our three questions, I would say, well, the position is always positive. The position is increasing. There's a positive slope. So that means that not only is the position always positive, but the slope, the velocity, is positive. And that slope is constant, meaning that the velocity is constant, meaning no acceleration. Let's take all of those and see how we can draw these next graphs. We just said that the slope of this graph is positive, and the slope of any x versus t graph tells us about the velocity of that object. If the slope is both positive and constant for the x versus t graph, that means the velocity must be positive and constant. So I would draw that like this. It doesn't matter where you draw it as long as it's positive and it's constant on this graph. That is what the corresponding velocity versus time graph would look like. Now, we know, and so we can get this last graph one of two ways. We said that the slope here is constant. It's not changing, which means the velocity is constant or not changing, and a constant velocity means no acceleration. So that tells me right now that that means the acceleration is 0, and you just do that by tracing this line right here. We could also look at the v versus t graph and say that, well, the slope of a velocity versus time graph tells us the acceleration. This line right here, because the velocity is constant, has a slope of 0, therefore the acceleration should be 0. And therefore, our acceleration looks like this. So this is a very simple set of graphs, and they all tell you pretty much the same thing. Now, something more complex would look like this, okay, where we have a positive acceleration and then a negative acceleration, and the switch is rather instantaneous. We can also work backwards with this. One of the important things is it says assume that x naught and v naught are both 0. And that's important because otherwise we wouldn't know where to start these graphs. So let's start them both at their respective origins. Now let's work backwards. So this time, in the first example, we worked forwards through the graphs. Now we're going to work backwards through the graphs. This acceleration is positive to start off and then becomes negative. And it's approximately equal amounts. Okay? The acceleration is positive and it is constant. Okay, that means the object, and if you think about it, the area under a curve for the acceleration, for an acceleration versus time graph, shows you the change in velocity. Since this is above the x-axis, this would be a positive change in velocity. This would be a negative change in velocity. Okay, if we're starting here at the origin, a positive change in velocity means the velocity must increase. And since the acceleration is constant, and the slope of a velocity versus time graph is the acceleration, and we know that's constant, we should have a constant slope over this time period. So maybe something like this. Okay, that is a constant positive. It's a constant positive slope for a v versus t graph, leading us to a constant positive acceleration. Then we have a constant negative acceleration, which should lead to a constant negative slope on my v versus t graph. Perhaps something like this. Okay? Again, constant negative slope on a v versus t graph means constant negative acceleration. That's what we have right here. We have a negative area for our acceleration versus time graph, which means we should be losing velocity, which is exactly what this line trace tells us. Last but not least, we can take this to the position versus time graph. Remember, the slope of a position versus time graph tells us the velocity. The velocity is constant, the velocity is increasing over this first half of the time, which means that our slope on the position versus time graph should be increasing. How do we draw an increasing slope? Well, it's a little tricky, but something like this would be an increasing slope. Okay, right about like that. Then, halfway through, our velocity begins to decrease. Okay, and if the velocity decreases, and the velocity is the slope of a position versus time graph, that means the slope should decrease. But notice, the slope should still be positive. The velocity never becomes negative. It never crosses that x-axis. The velocity never becomes negative, so the slope should never become negative. Matter of fact, the velocity gets back down to 0, and if the velocity is 0, then the slope of this graph should be 0 at the end. So then maybe that looks something like this. Okay, so we have a set of three graphs that again are related. And just to prove even more of a point, the area under a velocity versus time graph shows you the change in displacement, how the object traveled. Did it travel forward or backward? If there was area under this curve, it would show travel backward. All this area is above the curve, which means forward travel, and if you look, the object is always moving forward. It's always gaining position. Its displacement from the origin is always increasing. It never turns around and goes back towards the origin. Okay? We're going to look in the next set of videos at a whole bunch of other graphs that look just that are similar to this, where you've got one graph and you've got to predict what the other ones should look like. This is a very key. This is a key activity to do to get used to using slope and using all these rules that we've talked about, these 10 or so rules for position versus time, velocity versus time, and acceleration versus time graphs, to predict and kind of tease out how other graphs would look and to learn more about the motion. Okay? I'll see you later.